So we're going to talk for a few minutes about a mine reclamation project in the Pacific Coastal Forest biome. My name's Zach, and Amy, Jeremy, and Michelle will be joining shortly. The Pacific Coastal Forests stretch from southern Oregon to the tip of Vancouver Island. Cool, moist air from the ocean causes frequent clouds and fog. Because of the cool, moist conditions, these forests are some of the most productive ecosystems in the world. These forests are characterized by large, old-growth trees, and forests can start at sea level and grow up to elevations of 3,500 feet. The annual precipitation ranges from 60 to 130 inches, with higher coastal regions receiving the majority of the precipitation. These forests usually have warm summers and mild winters. The average annual temperature is around 55 degrees Fahrenheit. The vegetation community consists mainly of large Douglas fir and western hemlock, then shrubs, ferns, and mosses on the forest floor. There are multiple soil types within the biome, but our site mainly consists of inceptisols. These soils are moderately deep and contain a lot of organic material. Some restoration challenges are a change in fire regime, insects, and climate. For our restoration site, other challenges include heavy metals, toxins, and compacted soils. The New Bexton mine is formerly a mineral extraction mine. It is approximately 700 hectares. There are a few creeks that run through the mine and empty into a large river. There are tailings ponds that we have drained that left sediment with large amounts of heavy metals. Sediment can be picked up by the wind and transport toxic dust, settling in off-site locations. The site also has a heap leach pad that leaks cyanide into the soils and also compacted the soil. There is a school approximately 10 miles downwind from the site. Controlling the toxic dust to reduce pollutants in public areas such as the school is the #1 priority.
In order to restore the New Bexton mine area, we've set some objectives and goals to help guide us through the process. Our first objective is to mitigate the former heap leach pad damages. We're going to do this by reducing compaction, using deep ripping of the heap leach pad, and also the unnecessary roadways in year 1. We're also going to reduce cyanide concentration to acceptable levels using bioremediation in year 1. Our second objective is to mitigate toxic dust potential. We'll do this by utilizing wind barriers and cover vegetation to prevent further windborne toxic dust, and we'll reduce heavy metal concentration by 50% by planting hyperaccumulating species in year 1, followed by harvest. Our third objective is to promote native vegetation establishment. We're going to do this by establishing understory species in some trees to 50% cover in year 1, and then 75% cover in year 2. Additional planting of later successional species will happen in year 5. Now we'll take a look at the methods we'll be using to restore the New Bexton mine area. In regard to soil testing methods, the first thing we want to do is examine the topography in the context of climate, time, organisms, and parent material to assess the most important mechanisms of soil development. And as we examine the topography, we want to look for soil stability, erosion susceptibility, and moisture retention. This will enable us to identify areas that may dry out or need to be physically modified to avoid mass wasting, such as a landslide. Second, we want to identify the areas of the mining site most heavily influenced by compaction, as well as areas that contain the most heavy metal toxicity in the form of arsenic, cadmium, lead, and zinc. After we assess the area, it's highly important to mitigate further wind and water erosion, especially in places that have heavy metal concentrations that could be blown toward the school or transferred to streams. To mitigate wind erosion, we could potentially use windbreaks, a cover mulch, or cultivation, and to reduce water erosion, we could use a cover mulch, mechanical modification, or other crop practices. Performing an on-site assessment is crucial in determining microsite factors that delineate which methods will be the most effective. There's a few different activities that we'll perform in regard to soil remediation. Physically, we plan to mechanically modify some areas, such as the open pit, to revert them to a more natural topography. We also plan to use deep ripping on the heap leach pad, roadways, and other compacted areas. Chaining the bare soil in uncompacted areas will increase surface roughness in preparation for seeding. After the physical modifications are finished, we'll use bioremediation with bacteria species at the heap leach pad to reduce cyanide concentrations. Lime will be applied to tailings ponds to reduce acidity. Then mulch will be added to the heap leach pad and the tailings ponds to reduce further wind or water erosion, provide essential plant nutrients, and stabilize the soil. Biological additions will include seeding various nitrogen-fixing legumes and adding earthworms to formerly compacted areas. To understand how our interventions are impacting the area, we'll conduct biannual assessments across the site, as well as additional assessments before and after interventions. Where wind and water erosion may still be occurring, we'll determine if physical modification is necessary, then add immediate mitigation such as straw wattles, or list the area as priority for revegetation at the next available planting date. We'll also want to monitor bulk density and water infiltration at formerly compacted areas to determine whether additional tilling or organic matter application is necessary. We want to make sure that soil chemistry is progressing by measuring pH levels and heavy metal concentrations in the soil. If toxins are decreasing slower than we anticipated, then we'll push back seedling planting in those areas and prioritize hyperaccumulator species to be planted and harvested there. This is a list of some of the species we'll be planting at the site. Sunflower and alpine pennycress can both be seeded in the tailings pond areas and will hyperaccumulate their respective heavy metals. They can be harvested in the fall to remove the toxins from the underlying biogeochemical processes. Pacific willow is good for stabilizing stream banks as well as providing resistance to any cyanide left in the soil after bioremediation takes place. Common beargrass can be seeded across the site to encourage stabilization, and ponderosa pine and western hemlock can be planted across the site to help encourage the reestablishment of the native community. We chose these as our focal species for several reasons. They're tolerant to metals in the soil, and some will be helpful for mitigating these toxin levels. They're also hardy once established, so they shouldn't be outcompeted by potential invasives and will efficiently propagate on their own. They're native to the moist climate and will help reestablish a native plant community that will fit into the surrounding landscape. Because this site will potentially be used for recreation in the future, some roads are going to be left to provide accessibility. In addition, as water quality improves, fish will help keep destructive insects at bay. Two of the things that we want to pay attention to when monitoring the vegetation are the minimization of dust and toxins and increasing shade. If the grasses, forbs, and especially the pennycress are not covering a majority of the ground, then we're planning on replanting each spring until ground cover is at 75%. If less than 50% of the planted willows and ponderosa pine established by year 3, then we're planning on replanting these species and also pushing the planting of the hemlock back 2 years, since hemlock requires shade. This is a timeline for the New Bexton mine site restoration activities. Site-wide soil testing will happen twice per year, once before any interventions occur and once in the fall. This will help us see changes in the soil and how quickly they're occurring so that we can adjust accordingly. Preliminary soil remediation will take place immediately after soil testing. This includes bioremediation, deep ripping, liming, and mulch applications. We'll do our planting and seeding in the spring to minimize predation from granivores. We'll plant the hemlock in later years once the necessary shade is established. Maintenance such as watering and weeding will take place over the summer as plants are growing. We'll also monitor on a monthly basis over the summer to see how well plants are establishing. Each winter, we'll write up the results of the year, analyze them, and adapt our plan accordingly so that we can achieve a characteristic community on the restoration site as soon as possible.